Okay, it's time to begin. I believe everyone is here except for Tioni. I'm probably still mispronouncing his name. So, let us get started.
Tioni? His name is Tioni.
Okay, so I did pronounce it right then. Okay. We've had this before. That is, Newton's second law tells us about acceleration. Acceleration is the change in velocity divided by change in time. Velocity has both direction and speed. So an acceleration can be a change in speed or change in direction. You guys remember talking about that? Okay. I bring that up because we are going to be looking at things like Newton's universal law of gravitation. Now, going as far back as I think a week and a half ago on Friday, you looked at Newton's universal law of gravitation. And so you understand that the gravitational force, this minus sign, is really just there to remind you of the direction. There's no vector sign here, so without having a vector sign, it's not very useful. But the gravitational force is always attractive, always pulling objects together, never pushing them apart. The reason gravity is the one I consider the most important force in astronomy is because when you get to very large distances, things like the electromagnetic force goes towards zero because you have repulsion and attraction, and it starts adding up and balancing towards zero. But with gravity, it's always attractive, so the bigger you get, just the more attraction you have. Although we did learn inversely proportional to distance squared. So that means as distance gets bigger, the force gets smaller. So we've seen this equation. I think I've even asked you simple questions like, why doesn't Margaret feel the force between her and Lauren Lee? Remember I did the example with the three of them and double the distance and it's 1/4 of the force. Why doesn't Margaret feel that force? Or why doesn't Lauren Lee feel the forces of both of those young ladies pulling her?
It takes a very, very hard amount of math for you to feel the force.
Okay. I like the way she says the force, like we're talking Star Trek or Star Wars. You see how good I am in my Star whatever lore. The force has this constant G that's what, 6.67 times 10 to the minus 9, I think. Newton meters squared per kilogram squared. I didn't look that up. That's just going from what I think it is from, a year ago. But that's a very small number. And so unless the separation is really tiny, like, if you had two humans and their centers were separated by, let's say, a millionth of a meter, well, sure, yeah, there'd be some measurable force there. But of course, you can't get two humans, so their centers are separated by a millionth of a meter. You've crushed them at that point, and it's useless. The masses of the humans are on the order of 100 kilograms each, so this here is going to be on the order of 10,000 on top. But 10,000 times 10 to the minus 9 is still 10 to the minus 5. Very, very weak force between humans. But we feel a very strong gravitational pull between us and the Earth. Now, we're a long ways away from the center of the Earth. This R is the distance between my center and the center of the Earth, if I'm talking about the Earth. That's a big distance. We all agree, right? But the mass of the Earth is enormous. And since it's so enormous, it's still a very strong force. And so the force of gravity is, I think, the most important force in astronomy. It's that force that can explain things like how the moon orbits the Earth, how the Earth orbits the sun, how the sun orbits the Milky Way galaxy center, how the Milky Way galaxy is interacting with other galaxies. You may not know this, but the Milky Way galaxy is right now gobbling up the Sagittarius dwarf galaxy. There is a galaxy that is interacting with our galaxy, and its stars are being flung about, and eventually most of that galaxy will be part of our galaxy. Some of it will be thrown off and just on its own, which is totally cool, right? And it's all governed by gravity. Now, let's talk a little about gravity. I think I cut out all of the pretty pictures. I cut out all the pretty pictures. So let's talk a little about gravity and about what Newton did with gravity. First of all, what was the whole Newton's apple thing about?
He was sitting in the tree, an apple fell down, and went away when apples fall.
Okay? That's the simple story. Now, we should clarify, at least as far as documented history goes, that's a story he told. Not necessarily a true story, but a story he told to illustrate the point. That he's sitting there under the tree and an apple falls on his head. And he says, wait, why did the apple fall? And according to Newton's second law, it will accelerate, which means change velocity. It was stationary up there and then it started falling down, so it accelerated. It will accelerate only if there is a force that's making it accelerate. And so he said that must have had a force that was pulling it down from being in the tree, which sounds very simple and non-special to us. But to his time, that was really a bold idea, because they thought the only way I could ever put a force on Lauren Lee's phone to make her stop playing games in class is to come and push on it. If I touch it, then I can put a force on it. Force is anything that pushes or pulls. But being able to stand out here and going, right, that kind of force we don't have control of. And what he was saying was there must be some force at a distance that made the apple fall on his head. And so that force we call gravity. And then he said, now wait a minute. So if that apple up in the tree has a force of gravity that's going to make it fall down, then what about the moon? The moon is out there. There should be a force of gravity between us and the moon. And what should that make the moon do?
Should fall.
It should fall. And so then he had to ask himself, why doesn't the moon fall? And his explanation goes like this. I have this ball. I roll it off the desk slowly. Where is it going to land? On the ground, close to the desk, right? Well, if I make it go faster, it lands way over there. So, of course, he knew that the Earth was shaped like a sphere. And he said, if it's going fast enough, if the moon is going fast enough, it can constantly fall but miss the ground. And so the moon is constantly falling toward the Earth, but instead of getting closer to the Earth, it's just changing direction and orbiting around the Earth. And so that's how we now understand gravity makes the moon orbit around the Earth. That force of gravity is pulling it in. If there was no gravity, what would happen to the moon? Yeah. It would just go bye-bye. It would just go in a straight line and zip away from us. But gravity is pulling it toward us, making it go around in a loop. So Newton's first law, object staying constant motionless, acting on force, says that the moon would just take off. But his second law says because there's a force, it's accelerating and changing direction is what's happening from that acceleration. So that brings us to this picture. And I just realized my favorite demonstration that I looked for last class period, I did not go and locate it. It's still not here. My favorite demonstration is simply a bob tied to a string that I swing around my head and then I throw it, right? It's a lot of fun. Takes me back to when I was a little boy in Liberia and we had our slingshots and throw things with a slingshot and we thought we were, oh, so cool. True story. The ladies there work very hard, and one of the things they have to do is keep the birds away from the rice. And so they put, or at least they did back when I was a kid, they put like coffee cans distributed throughout the rice fields. And then when birds would come, they would use their sling and throw a rock and hit the little coffee can near where the birds are to scare them. Which is pretty good aim, right? Pretty impressive. Anyway, we use that to illustrate why the moon goes around. If something is going in a circle, it has to have a specific acceleration to make it go in a circle. That acceleration we call the centripetal acceleration is speed squared divided by the radius. I use d because they use d here, but d is the radius of the circle. I know it looks an awful lot like diameter, but it means distance in this case. We call that centripetal acceleration, the acceleration necessary to go in a circle. Does anybody know what the word centripetal means?
It means around the center.
Toward the center. Centripetal means toward the center. For something to go in a circle, you need an acceleration toward the center that's equal to the speed squared divided by the radius. So if something's going in a faster circle, it's going to need a much higher acceleration toward the center, which means you're going to have a force pulling toward the center harder to make it stay in the circle. And you'll notice also, as the radius gets bigger, as d gets bigger, then the force you need is smaller. So the force necessary to make something go in a circle we call the centripetal force. And the centripetal force is actually adding up all of the forces toward the center. So in my picture here, since I don't have my string to swing around my head, if you look at this picture, what is putting a force on that ball?
The guy's pulling it.
Okay? So directly, it's the string. The guy's pulling the string is pulling on the ball. And that string, you know this answer, what direction is the string pulling on the ball?
Toward.
Inward. The force of a string is actually always parallel to the string in the direction the string is leaving. So you have a force going toward the center here that we call the force of tension. And so, using Newton's second law, the sum of the forces toward the center must be equal to the mass times the acceleration toward the center. Acceleration toward the center, right there. All of the forces acting out toward the center is just the force of tension. And that's how we get the equation they showed there. Now, how does that play in with things like the moon orbiting the Earth? Come on. With the moon orbiting the Earth, we have a distance, of course, of 1 astronomical unit. That's the radius. That's the distance between the Earth and the moon, or Earth and the Sun in this case, if it's 1 astronomical unit. And we have the Earth moving. Notice how fast the Earth is moving. Would you consider that fast or slow?
20 kilometers per second. I mean,
Well, between friends, we round out to 30.
That is fast.
That's really, really fast. The Earth is really booking through space, which is why we have meteor showers. When the Earth comes and hits a cloud of debris left by a comet, all that debris is hitting the Earth's atmosphere at that speed relative to the Earth. And so, as you might imagine, when you have something really fast hitting the Earth's atmosphere, the collisions make the atmosphere around it and that object heat up. It's very, very hot. And you actually have electrons excited because of that, and you see the light from the excited electrons. Okay, so the Earth is booking around the Sun at a speed of roughly 30 kilometers per second, a distance of 1 astronomical unit, and the force between the Earth and the Sun is given by Newton's universal law of gravitation. Now, if we take this and we combine it with the sum of the forces toward the center is the mass of a circle with a plus in it times v squared over d, we have Newton's second law. Now, what does a circle with a plus in it mean? That means Earth. That's your scientific symbol for Earth. What about a circle with a dot in it? What do you suppose that means? Sun. The circle with the dot is the sun. So when you see these, the circle with a plus in it, that's the Earth. Circle with a dot, that's the sun. So this is mass of the Earth times mass of the sun. So taking this relationship, actually, I should have gone ahead and put here A sub c in the first line. And then making my substitutions, g mass of the Earth, mass of the sun, over the separation squared must be equal to the mass of the Earth times v squared over d. Now I have a relationship. I can cancel the mass of the Earth. Right, I have mass of the Earth there and a mass of the Earth there. And so I can solve this, for instance, to find how fast the Earth has to be going for its distance from the sun. Or, yeah, let me actually do that. Solving this for v squared, I just have to multiply both sides by d. course, this d is going to cancel one of those. And unless I made a gooberish mistake, which I didn't, that's the equation for the speed the Earth has to have to orbit the Sun at a distance d. Now, the speed can be written as the distance the Earth travels in a year, the circumference 2 pi times, it's 2 pi times diameter, or no, yeah, it's 2 pi times diameter. Okay, my brain has gone sideways. 2 pi times the radius, and d stands for radius, divided by the time for a year, which we call the period. We know a year is 1 year long. So if I take this relationship and substitute it for v, I have 2 pi d over the period quantity squared is equal to g, whoops, I forgot to cancel this right here. That should not have been there, my mistake. That was already canceled and I didn't see it. G, mass of the Sun, over d. Now I'm going to, go ahead. Because I had an M Earth here and an M Earth here.
Oh, yeah. Gotcha.
So I take this relationship, and now for my final trick, I'm going to solve it for, oh, I don't know, M. No, let me solve it for d. I'll solve it for d. So on this side, 2 squared is 4. Pi squared is pi. D squared is d over p squared. To solve for d, I'm going to have to multiply across. And I'll have d squared times d is d cubed. So I have d cubed is equal to g times the mass of the Sun over 4 pi squared times the period squared. Now you look at that and you don't have to be able to do the math there. But you look at that and you see what that says is the distance between the Sun and the Earth cubed is proportional to the time for the Earth to orbit the Sun squared. We've seen that before. Anybody remember where we saw that before? No? Seen what? This equation here. We saw this equation here before, except this part here was not written there. We learned that the semi-major axis cubed in units of astronomical units was equal to the period of the orbit squared in units of years. That was Kepler's third law. So Newton's laws, his universal gravitation and his second law of physics, combine to give us Kepler's third law. Why is this important? Kepler's third law was based on observation only. He observed the motion of the planets and he came up with this law. But now we have a reason, a scientific reason why that law should be true instead of just we observe that this is true. And as physicists go, we're trying to explain why things happen. So having a reason why it happens instead of just the observation makes it much more sound. Yeah?
Can you scroll back up and get quite all of this?
Which part?
A little further. Just the first equation.
So sum of the forces equals mass times acceleration. And then I substitute for force, the force of gravitation, and for acceleration, v squared over the radius, where d is the radius. So, Newton's work, the upshot of all this, Newton's work gave us a relationship to predict Kepler's laws. So Kepler's laws now have a solid foundation. If I come back and take that self-same equation I had done before, and I solve it for mass, I can find that the mass of an object is the separation times the speed squared divided by that capital G. So if I can measure the speed at which something is orbiting and the distance away for its orbit, I can determine the mass of the object it's orbiting. Note in my equation down here, this was the mass of the sun. The mass of the thing that we are orbiting, not the mass of the Earth. So it doesn't matter if we were to take the Earth or replace the Earth with Caleb. It would have exactly the same period for the orbit because it's only the mass of the sun that we're orbiting that matters. Likewise, if we replace the moon with Caleb, it would orbit, Caleb would orbit the same period the moon does. Or to put another way, we don't worry about flying off of the Earth because we're at the same orbit as the Earth. We just are both going along. If the sun wasn't here, what would happen with the Earth? We'd fly away in a straight line. But we're orbiting the sun because of gravitation. So, this, and I'm not going to do any more derivation, this is taking that same equation and doing it a little bit more carefully. This is doing a little more physics than what we're going to do in this class. But it turns out that when the Earth orbits the sun, the Earth isn't the only thing that's moving. The sun is also moving. You could say that the sun is orbiting the Earth. Although if you want to be super accurate, you say the Earth and the sun both orbit the, quote, barycenter, B-A-R-Y. The barycenter is the center of mass for the Earth-Sun system. And so, say the sun is here and the Earth is here, the barycenter is here. And both the sun is orbiting that barycenter and the Earth is orbiting that barycenter.
They're tugging at each other.
Yeah, because the Earth is tugging on the sun with exactly the same force the sun's tugging on the Earth. The sun doesn't accelerate nearly as much. Why doesn't the sun accelerate nearly as much? It's more massive. But it still does. So the sun is also doing an orbit.
So then what happens when you combine that with, say, for example, you've got 7 more planets?
Mm-hmm.
So then that center would be a composite of all of those?
Yes. And in fact, this is... Do you have a question? Okay. Have you guys heard the word exoplanets? One has. Exoplanets are planets that are orbiting stars other than our sun. Now, we can observe planets orbiting our sun fairly easily, for the most part. But to observe planets orbiting another star is very difficult, right? The nearest star is more than 4 light years away. So how do we observe those planets orbiting the star? One method is to look at the wiggles of the star caused by the orbits. Because the sun and the other stars, because the sun's just a star, do little wiggles, and you can look at the wiggles of the star and determine how many different objects are orbiting by how many different periods you see meshed together in it. And you can determine what the different periods are for the different objects. And from those periods, you can determine what the masses are. And so that's one of the ways of searching for and discovering exoplanets, is looking at the wiggles of the stars caused by the planets orbiting around them. So this equation is really important. This equation allows us to determine the masses of stars mostly. Why stars mostly? What's the relationship between, or how do you compare the mass of the star with the mass of a planet? Okay, which one?
The star. The star is smaller than the planet? No. Oh.
The mass of the star is, well, neutron stars are still much, much more massive. They're smaller, but much, much more massive. So the stars are far more massive than the planets. Hence, if you take the sum of the mass of the planet and the star, let's say you're taking 1,000,000 plus 10. Between you and me, that's still 1,000,000, right? If I had $1 million in my pocket and I lost a $10 bill, I'd still say, yeah, I got $1 million in my pocket. Right? I wouldn't say, oh man, $999,990. So close. So, what was that?
I would real quick get $10. Say that.
So, we usually can use this to find the mass of the star, the more massive of the two objects. But that's an important equation because of what it allows us to do. Determine masses of things out there that we have no way of putting on a balance or anything like that. Now here's a picture showing Newton's idea for orbit. He's saying you have a cannon, you fire the cannonball, you fire it, it goes a distance and hits the ground. You fire it harder, and it goes a farther distance before it hits the ground. Because the Earth is a sphere, if you fire it hard enough, you can make it so it just goes around in a circle. And so, using our physics, we come up with two equations. The speed an object has to have to go in a circular orbit is square root of g times the mass of the thing being orbited, not the mass of the orbiter. So if we send a spacecraft up to orbit the Earth, the mass of the spacecraft doesn't come into this calculation. It's only the mass of the Earth. And this r is the separation between the center of the object being orbited and the orbiter. So that's the equation for circular velocity. What happens if you make something go faster than the circular velocity?
And then become the escape velocity.
Well, there is something in between. You go faster than the circular velocity, it's going to get farther away. But then, of course, Kepler's first law said that things orbit in circles, or not circles, ellipses. And so it'll get farther away and then it'll come back in. And so if you increase that speed, you'll start making it do an elliptical orbit. And so you can have, if you lower the speed, you'll have an ellipse that comes closer over here. Circle, bigger speed, ellipse. If you keep increasing, then you get to the point where you have a parabolic arc. That is, it comes in. I'll show a parabolic orbit example here. Parabolic orbit goes.
Like a parabola.
Well, yes, like a parabola. What's the key to a parabola? These two lines are asymptoting parallel. Anything slower than that, and they would come back in and you'd form an ellipse. So that's a parabolic arc, which starts with a P, not an R. I am pretty sure that's not spelled right. Yeah, it is right. Okay. Or we can have a hyperbolic arc. A hyperbolic arc goes like this. Those are not parallel. That's the difference in the hyperbolic orbit and the parabolic orbit. The hyperbola, they're asymptotic to straight lines that are non-parallel. They're diverging. So at just the right speed, at the escape velocity, you'd have that parabolic arc. And if you go faster than that, you'd have the hyperbolic arc. Now, this is really useful, and I think I have a picture for this, I hope, for sending out spacecraft. We send a spacecraft like, let's say, the, New Horizons that has recently passed by Pluto, and will for the next year be streaming information as fast as it can for the scientists to analyze from its short, 3-day flyby. When we want to get it out there, we have to start from Earth. So we start by saying, well, what's the escape velocity from Earth? How fast do we have to make something travel to get away from the Earth? And we can calculate that using our equation. Escape velocity is square root 2gm over r. Now, if you think about this, since it's square root 2gm over r, what happens to the escape velocity as you get farther away from the Earth? As r gets bigger. It gets smaller. So one of the things you can do is, since the air resistance is pretty big here near the Earth, if you get it out there further and then give it increased speed, it'll actually be more effective. So you have burns that burn for a while. You don't just use a slingshot and shoot it from Earth. You have a rocket that's going to keep giving it thrust for a while, and then you get up here and less atmosphere, it's more effective. Other things you probably have never thought of. How many people have watched a space shuttle launch on TV? I'm not going to say live because I'm pretty sure that's going to be zero. If anybody's got live, then You have?
Yeah.
I'm so jealous. 2 of you.
I'm jealous too.
Yeah. I proposed when I was teaching at PUC that we should take a field trip to Cape Canaveral. We'd just, rent a van to watch a space shuttle launch. No one was buying that. Anyway, when they do space shuttle launches, have you noticed the peculiarity of what happens to the space shuttle after it takes off? You two who've actually been there, it takes off vertically, then what does it do? It rolls over on its back and goes like that.
Gravity? Is that why?
Well, first, what direction does it go? Goes what?
The direction.
Well, in terms of north, south, east, west.
I don't know.
Well, the Earth is rotating so that the sun comes up in the east, right? So we are constantly going toward the east. They lay it over so that it's traveling eastward. Why? Because the rocket's velocity is relative to the Earth, to the atmosphere of the Earth. And so if they can get going east, the direction the Earth is spinning, they're going to be adding the rotational speed of the Earth to the speed they have relative to the air. If they turned and went the other direction, they would be wasting energy. They'd have to get a lot more speed relative to the air to have the speed relative to the center of the Earth to escape. So they actually roll over on their backs and head east so that they can use the speed of the Earth's air to assist them in escaping. And as they go faster, they'll go farther and farther away from the Earth. And, the space shuttle actually doesn't escape the Earth. It just goes into a high Earth orbit. An orbit that's beyond the air, but it is still orbiting around the Earth. Obviously, the moon is also beyond the air, but still orbiting the Earth. I guess I don't have a picture for like the New Horizons I started with. Nope. Don't answer that yet. You can't answer that yet. You know what's coming next. A question. For the New Horizons spacecraft, they did what we call planetary slingshot maneuver. So what's a planetary slingshot? You have the sun, the Earth's orbiting around the sun. And then you go out further, you have Mars and Jupiter. I'm pretty sure that it did a slingshot off of Jupiter. So you have Jupiter out here. So Jupiter is going like this, and the Earth is likewise going like this. And so they have the spacecraft, and this is where rocket science to me really comes into play. They have the spacecraft so it does something like and comes up right behind Jupiter. So if it comes up right behind Jupiter and it's going fast enough, faster than the escape velocity, what kind of arc is it, or of orbit is going to have around Jupiter?
Hyperbolic.
A hyperbolic orbit. So it's going to come around Jupiter, and of course you come just behind it. If you come just ahead of it, you really messed up.
Somebody's being fine.
And so it comes around like this. It came in like this, goes out like that. But what did it do in the meantime? It essentially picked up Jupiter's speed as it did the slingshot. And so you add a huge amount of energy, a huge amount of speed to it by going around Jupiter. And so that's a way of picking up free energy. Now, of course, if somebody wants to really sit here and count the beans, that energy wasn't free. You took it away from Jupiter. So what do you do to Jupiter? You slowed it down by some unmeasurable amount, which means Jupiter's going to fall closer to the sun by some unmeasurable amount.
5 seconds.
Right. We're not worried about that. Yeah. It might be 5 seconds different between the time. Well, it just doesn't matter. And in fact, they do slingshots off of the Earth too. There are some, you look at their path to get out there for something like Voyager, and like it goes inside, takes a slingshot off of Venus, goes out, takes a slingshot off of Earth, comes back in, goes out. All of these to pick up energy so that they don't have to have as much fuel aboard. What does all this have to do with today's lecture? It's all dealing with that law of universal gravitation. That's what makes all of this possible. Now notice here we had the escape velocity square root 2 g, mass of the object being orbited, divided by radius. Circular velocity, square root g, mass of the object being orbited. Typo there. Divided by radius. That's straight from the text. Oh, I see. That's saying if we go out to 2 radius. So here's the one that's at 1 radius. It's confusing if you look at that one because it's for 2 radius. What's the difference in those 2 equations? The 2 that are in green boxes.
One has double the.
Yeah. One has 2 that the other doesn't have. So you have to go square root of 2 times faster to escape than you do to just go in a circle. Square root of 2 is 1.4. So basically 40% faster than the circular orbit's enough to escape. This escape velocity is important for a number of reasons, and one of them is I like to breathe oxygen. It's one of the things I really like to do. Whenever I can't, I get really panicky. So, how is it that I'm able to breathe oxygen? That is it. We have oxygen molecules, we have hydrogen molecules, helium molecules, nitrogen molecules. We have all of these molecules in the air. And temperature, and this is actually coming up in another slide, so I'll be able to skip over when we get there. Temperature is a measurement telling us how fast molecules are going. How many people in temperature measure how fast molecules are moving? Okay, good. Got a number of people. So the faster molecules are moving, the higher temperature. And so at the temperature of Earth, we can calculate the speeds for different molecules. Molecules that have more mass have lower speeds. Ones that have smaller mass have higher speeds. So hydrogen, if you look back there at the periodic table, hydrogen is the lowest mass element, the one in the top left corner. So it's going to have the highest speed. Helium over here, it has a mass 4 times the mass of hydrogen. So its speed is slower by, I think, a factor of about 2 than the speed of hydrogen. And so on. So you get to oxygen. Oxygen is molecular. It's O2. So it has a mass of about 32 times the mass of a hydrogen atom, which means its speed is significantly less than hydrogen atom at room temperature. Why is all this important? It turns out the escape velocity for the Earth is around 11 kilometers per second. That is, if you have a molecule at the surface of the Earth, and it's going 11.2 kilometers per second, it can escape. Hydrogen, actually hydrogen forms molecules as well, H2. The hydrogens are going faster than that at normal Earth temperatures. So what that means is the Earth can't hold on to the hydrogen, it's going too fast. And so we said bye-bye to all of our hydrogen. Helium is right on the cusp. So helium we do lose, but it takes longer. Things heavier than helium we can hold on to. So our atmosphere is dominated. Actually, do you guys know what gas dominates our atmosphere? Nitrogen. About 79% of our atmosphere is nitrogen, and the balance is oxygen, which is trace amounts of other gases. But we wouldn't be able to hold on to those if the Earth's escape velocity was half of what it is. We need it to be a fairly large escape velocity so we can hold on to those things. So if you take something like, Venus, well, not Venus, I didn't want to use that because Venus has a special situation. Let's take Mercury. Mercury gets really close to the sun. And so it gets really hot, which means that you have really fast-moving molecules. At the same time, Mercury has a small mass. You look at the equation there for escape velocity. Small mass means small escape velocity. Mercury can't hold on to anything. The moon is similar. The moon doesn't get nearly as hot as Mercury because it's a lot farther away from the sun. But it can't hold on to anything because it has a small mass. Mars has a bigger mass, and it has some atmosphere, about 1/100th as thick as ours. Venus is about the same mass as us, and it's closer to the sun. And so you think, okay, closer to the sun, it's getting hotter. It does. Temperatures on Venus are very, very hot. But Venus has an extremely thick atmosphere because it still has the escape velocity is higher than what is necessary for its primary gases, things like methane, to escape. And so Venus has an atmosphere that's 100 times thicker than ours. That atmosphere gives it a runaway greenhouse effect. It is hot everywhere on that planet at all times.
So what does this mean about the probability of places that humans could live in the universe?
Well, they call the places humans could live the Goldilocks zone, because you have to live in the region where the temperatures are such that you can, we believe, have liquid water. We think that's a necessity for life. And of course, you have to have a planet that in this region will also be holding on to atmosphere. So they, for any star, they can calculate, okay, planets have to be between here and here for it to be possible for there to be life.
And how long is it before we can figure out what stars have planets in that region? Because you said that we can figure out different planets.
Well, they are
variation of the sun.
almost on a daily basis, it seems, discovering more exoplanets. And so the number of exoplanets that's known, last time I checked was, of course, last year, and it was, I think, 1,400 exoplanets or something like that. I would guess it's around 2,000 by now. And it's assumed, we don't know this, right? It's not something that's been tested in any way. It's assumed that probably every star has planets. And then,
Found any in the Goldilocks zone?
yeah. And so, yeah, like you might have read about, was it Glyph? They give them a number, I don't know. With, you know, a planet that appears to be very Earth-like in Goldilocks zone. They're like, if there's life anywhere in the universe, there's a really good place for it. All right, so our clicker question. How does the escape velocity compare to circular velocity? In case you don't know this, 2 to the 1/2 is the same as square root of 2. I just couldn't put square root of 2 in this font, so I put it that way. Channel 33, of course. It shows you have an answer.
Good. Let's go through.
Okay, 25051. Okay, the two answers that garnered the most votes were that the circular velocity was square root of 2 times the escape, and that the escape velocity was square root of 2 times the circular. Remember, the escape velocity is when something escapes. Anything faster than escape velocity, it's still escaped. So the answer can't be v circular is faster than escape velocity. So it cannot be this one. It has to be that one. So most people at least remember that square root of 2. It's just where to put it that was confusing. Okay, geosynchronous orbits. Many of us have things like Dish Network or DirecTV, where we have a dish sitting in our backyard that's pointed up into the sky. How many people have aimed one of those things? Okay, I got 3. When you aim that beast, does it ever cross your mind, what am I aiming at? Sky. What you're aiming at is a satellite over the equator that is orbiting the Earth at exactly the same rate that the Earth is spinning. And we call that a geosynchronous orbit. Now, it turns out from the work we've done, there's a specific radius, a specific distance away from the center of the Earth that a satellite has to have to be in geosynchronous orbit. So that means that there is essentially one belt going across the equator above the Earth where all of your geosynchronous satellites are. Just a little quick thinking says those must be valuable. Because everybody wants to have things to communicate all over the earth. And those places are places where you can have a fixed dish. You don't have to sit there and have the dish changing where it's pointing. And so they have very carefully allocated slots on that geosynchronous orbit at the radius you get by calculating this here. Notice the geosynchronous radius is g times the mass of the object being orbited. So for Earth, that'd be the mass of the Earth, times the period over 2 pi quantity squared, all cube rooted. Once again, I couldn't figure out how to do a cube root. I spent a while and just couldn't figure it out. So that's another way of writing the same equation. And so all those slots have satellites. Well, they don't all have satellites in them, but most of them do. And then other people have come up with some really bizarre ideas. I think it was XM Radio decided, it was either XM or the one they merged with, which was Sirius. They decided, let's do something different. Let's put a bunch of satellites up there and let's put them in elliptical orbits. And we're going to have them, you know, the part when they're out there, they're going pretty slow because they're farther away from the Earth. And so we're going to adjust these things so we have, I think it's like 3 of them, and at any given time, 2 of them are over North America. And then you just have your receiver those antennas are non-directional that you have for that wavelength. And you have these 2 satellites, you should be able to pick up at least one of them if you're in North America at any time. And so instead of having to pay for those expensive geosynchronous orbits, they have these elliptical orbits that give them a trade-off, this one, then this one, then this one, going around to which one you're going to use.
Like mobile cell phone towers.
Yeah. Now, one more thing that's kind of cool is the global positioning system. Our global positioning system, who do you think invented the global positioning system?
The United States.
The United States. And specifically, what part of the United States paid for it? The military. A very large amount of our advances in science come from military funding. Why would the military want GPS? Well, so they can kill people. So they can target people. And so this GPS system, when it first was put into place, it was only usable by the military. And then they gave people the ability to partially decode. Now what you have with the GPS system is you have a number of satellites, I don't remember the number, 20-odd, 23, something like that. But you have these satellites that are orbiting the Earth, and they have very well-defined orbits. So it's very easy. You have simple equations to calculate where each one of those satellites is at any given time, because we know Kepler's laws govern the orbits. And then you have a little radio receiver that picks up signals from as many satellites as you can. And the signal from the satellite essentially says, "Hi, I'm Bob, and it's 5:33 at the beep." Beep. That's essentially what they're doing. They're sending out a communication that says who they are and what time it is. And your GPS system gets all of these different signals from the different satellites saying who they are and what time it is. Your little GPS radio knows what time it is where you are, and it calculates then how much time difference between when that signal was sent from the satellite and when you received it. From the time difference, it can calculate the distance to each of the satellites. And as soon as you have 3 satellites, you can triangulate to either above the satellites in a specific position or below the satellites in a specific position. I think we're all pretty good with we're below the satellites. So if you have 3 satellites communicating, you can exactly locate your position. Now, the government made it so we could partially use it, and then as things got more common, they went ahead and opened it up. So now we can use our cell phones that have a little GPS radio, perfect, little GPS radio, to figure out where we are any old time we want. If we had a wartime thing where somebody was targeting the U.S., you know what happened to our GPS? it would no longer work because the government would switch the way the times are made. They use a scrambled thing for time, so people can't decode what time it is and thus can't decode the positions. Because if it's wartime, they don't want somebody else using our GPS system to target us. And that's why other countries are coming out with their own GPS systems, so they aren't reliant on us for targeting and then we turn it off on them. Okay, apparently we're done because my tablet disconnected. Yep.
Wow.
So I'll see you for lab mañana.
Is that your pictures?
No, those come from Google.